All right. Okay. I hope you hear me. Yeah, thanks everyone for being here. Yeah, at any point in time, feel free to, or in the beginning, maybe reevaluate where you're sitting. I realized I was in the back for the last talks, and I couldn't see the slides very well. So feel free to just get up now and move to the front. So I'm Nathanael. I'm a PhD student at the University of Tübingen. I'm basically at the end of my PhD, so I'm handing in next month, hopefully. And in my PhD, I worked on probabilistic numerics for differential equations. And well, in the first months, even when I started getting to know these methods and implementing them, I implemented them in Julia and found that to be very pleasant and worked on this library since 2020, I guess now. So I'm very happy to finally be able to present it here at the JuliaCon. Maybe before I start, just to get an idea of who the people are in the crowd. So does anyone use differential equation solvers regularly? Okay, that's almost everyone. Amazing. Who knows what a Gaussian process is? Okay, it's the same people. And who knows what a Kalman filter is? All right. Okay, I think I can skip many of the slides. So we do probabilistic, or maybe who knows what probabilistic numerics is? Okay, it's still quite a lot of people, but half the people. Okay, so I will introduce probabilistic numerics and motivate probabilistic numerics by first talking about ordinary differential equations and how we typically solve them, and then point out what specifically the thing is that we try to do in probabilistic numerics. So when we have ordinary differential equations, so an equation like this in math, I've seen that this talk is tagged as math, so I'm allowed to put formulas. So we describe the derivative of some unknown function y with some equation, y dot equals f of y. F is called the vector field, so by evaluating f, we get information about the derivative of y. And if we also have an initial value, then this typically describes one function. There's one true solution to the ODE, and the goal, vaguely speaking, is just to find it. Visually, if we have, well, a very simple example, a logistic ODE, that means we have the blue dot, we have the arrows in the back, we want to find the black line. Because if we follow the arrows, then there's only one black line that comes out. And now in the logistic ODE, that's easy to do. We can just solve it in closed form by hand. But when we have a numerical, or when we have more complicated ODEs, we cannot do that anymore, so we use a numerical method. And most of them operate, at least for ODEs, they operate in a very similar way. So first of all, instead of describing y, I describe y hat, because this is now an approximation. And then we also discretize time. So they are typically some recursive description of how to go from one point in time, y hat at t, to a future point in time with some step size h. And here, in the case of the forward Euler method, where we just extrapolate along the gradient, backward Euler makes the whole thing a little bit more complicated because it's implicit, so you use an additional numerical method on top. Runge-Kutta and multi-step methods do something a bit more complicated because they extrapolate in a smarter way. But in the end, they all describe a y hat, they all discretize time in some way, and they all evaluate the vector field in order to construct this solution. And while they give you a y hat, it's still a reasonable or a meaningful output in the sense that in the limit, where if you make the step size small, you get the true solution. So the smaller the step size, the closer the red line is to the black line, so that is good. But at the same time, the red line is never actually the black line. So even if you make, for any finite step size, there will always be a difference. And you can see it for large steps, you can see it directly. For small steps, you might not see it, but there's still some numerical error. So in some sense, this initial task of finding y, you failed because the red line is not the black line. So if you put all your belief into the red line, then this is not actually the system that you're solving. And so that's where this probabilistic interpretation starts. So there is some unknown function y that we try to estimate. So this is an estimation problem. And we use information to estimate it, which is this vector field evaluation that we do along the way. And so in probabilistic numerics, what we do is we write it down as an estimation problem. We treat it as an estimation problem in a Bayesian way. And so in the end, we get belief over what we think y of t is. in a probabilistic way, because I mean it could be many different things, because there is some error, but we get, well, a probabilistic description of what we think it is. So we treat ODE solving as the Bayesian state estimation problem that it really is. At least that's what I would like to motivate. And so one quantity to look at is, I would argue, is this one, because it now describes the thing that we actually try to compute when we use a numerical method. Before that, I had the mathematical description and this mathematical ideal object that we would like to have. This is a bit more practical, because we might be able to compute that. So we want a belief over y of t such that it satisfies the initial value, and it should satisfy the ODE, but we're fine if the ODE is only satisfied on a discrete set of points. If you take infinitely many points, then this object should be similar to the object that we described before, but infinitely many data points is something that's hard to work with in the same way as solving an ODE exactly is hard to do. So how does this object look? Before I explain to you how to get it. So this describes a probability distribution over y. So assuming we have it, I can sample from it and plot samples. So I did. These are the samples. They're just so close together because the numerical error is small in this case, because logistic ODE is trivial, that you cannot see the individual green lines anymore. But if I plot the individual green lines in the space of y dot minus f of y, then I see that they look like this, and this gives you an idea of what's happening. So I conditioned this process on the fact that on a discrete set of points, this residual should be equal to 0. In between the points, who knows? And this who knows is basically, well, whatever probabilistic model you choose. That's what we do in Bayesian inference. So to get this, I chose some model, conditioned it on these zeros. In between, there's something happening according to my prior, and then this is the posterior in solution space. Okay, so very briefly, what kind of models are we using? So we use Gaussian processes. We actually use Gauss-Markov processes. I don't know how familiar you are with this topic, but if you know Gaussian processes, the standard thing that always comes up is they are cubic in the number of data points and expensive and so on. Our input is time, and so if we also put the Markov property in a GP, then it turns out inference is fast and exact. Then to do Bayesian inference, so we need a prior, we need a likelihood, and we need an inference algorithm. The likelihood is basically whatever is to the right of this bar, so that's the stuff that we want to condition on, which in our case is not even some noisy observation, it's just an equality constraint. So it's a bit of a stretch to call it an observation model, but that's how you implement it. We also often call it an information operator because it's kind of this virtual self-made data, I would say. So it's rather information that we impose. And well, you can see that this equation is here. We just put everything to one side and say it's equal to 0. And this also is equal to 0. So the left side depends on y, the right side does not. So the right side is the data point and the left side is the measurement model. Same for here. And then if you take these two things together, what you have is, so you have a continuous model that describes some state. You have a discrete observation model on the data points, well, on the times that we chose. So this problem in filtering and smoothing is known as a continuous discrete state estimation problem. And I can strongly recommend, well, there are books by Simo Serke, I think, is quite well known, on Bayesian filtering and smoothing and many things on this topic. But, well, you can solve this, vaguely speaking, with Bayesian filtering and smoothing and any algorithm that you find in there, which is, well, the extended Kalman filter is what we use mostly. If the ODE were linear, it's just a Kalman filter. You can use uncentered filters and so on. And so, well, to describe this visually again, so the priors typically look like this. It's super uninformed. It's an integrated Wiener process prior. If I take each of these green lines, I can squash them again through this residual function, and then it looks like chaos. And then once I do inference, I condition all of these orange lines onto the blue dots. And by doing that, the green lines collapse onto the ODE solution. And the magic to get from one to the other is extended Kalman filtering. Yeah, maybe just briefly, this is pseudocode on how this ODE solver looks. I did not introduce these symbols. Those are basically the prior. But here's the ODE and here's the time discretization. And just to give you an idea of what algorithmically happens, there's also, again, some loop that lets you go from left to right in the ODE. And then if you ever implemented a filter, there's typically a predict step and an update step, and you just iterate both. You predict, you update, you predict, you update. This code is actually very close to what you can implement in Julia in order to get something that solves ODEs. If you're curious about it, I have a URL here. You can find it on my GitHub, where I gave a 90-minute tutorial in Julia to people that do not know Julia, and still in 90 minutes they were able to implement basically this to solve ODEs. So to get a working example is really, really, really doable. So if you're curious, I would encourage you to, if you're curious about learning about the method, I would encourage you to implement it yourself. Of course, for using, there's the package. Maybe this works. Videos get more complicated. But then if you look at what happens, then again, the ODE solver solves the whole thing from left to right the same way as you would, as your standard Runge-Kutta method does. So it is algorithmically really similar to solvers that you know. And at each step, there's this extrapolation happening and then an update happening. But since we have a probabilistic model, we can also extrapolate into the future, which is what I've shown here. So everything that happens towards the right is basically according to the prior, given the current state. All right. And so what do you get when you do this? This is, I think, from the README of the package. So when you solve an ODE with these methods, and I will show to you how, then, this is a Fitsunagumo ODE, I think, just one of these standard problems. Then you get your standard ODE solution, U of t, it's typically called in the SciML context. But then inside this object, there's also uncertainty estimates that describe the numerical uncertainty of the solution that you can just access, because each of these things is basically a Gaussian, so you can plot the standard deviation, and you see that numerical error spikes roughly in these areas where the orange line is steep. That's when the orange error spikes, and it decreases again afterwards. Maybe this is an interesting thing to look at, because if you come from numerical analysis and you think about numerical error, often people think about worst case error and this idea that error always accumulates and so on, but that's not actually the case. So imagine if you have an exponential decay ODE, the numerical error goes to 0 because the solution just decays. So numerical error can go down, and it does. So this error is the thing that the method believes the error is that itself actually made. So it's a different object than this worst case exponential error. And I would argue it's more useful because it's what's actually happening. Okay, I have one slide for the skeptics, I would say. So I quickly explained this this method that is an ODE solver that maybe, at least half the people here don't know. So is this actually an ODE solver? And yes, so people in the group that I did my PhD in and other groups in the UK, for example, worked on these methods and have shown that these are actually ODE solvers because they have convergence rates. So I think this is maybe the biggest checkbox that you need to satisfy. If you make the step sizes small, the mean converges to the true solution and the uncertainty converges to 0. So eventually it does the correct thing. So this is very important. Then if you care about stability, you can look at stability of these methods. These are A-stable or they're L-stable versions. There's a connection to classic ODE solvers, if you know about multi-step methods. Maybe one point to linger on a little bit is how complex are these methods from a theoretical perspective. So since we use filtering and smoothing, they are linear in the number of time points. So not the bad GP case, but actually what you would expect from an ODE solver, which is why it's not even written here. But if your ODE is d-dimensional, then it's either linear in the dimension or cubic in the dimension, depending on if you use a version that is semi-implicit or an explicit version, which is exactly what your standard Runge-Kutta method is also complexity-wise. So an implicit Runge-Kutta method is also cubic, which is why solving stiff implicit large dimensional stiff systems in large dimensions is non-trivial. We have the same problem, but also the same linear scaling. You can do step size adaptation. It's implemented in the package also. Yeah, we did a parallel in time version. This I only talk about ODEs, but this idea also scales to higher order ODEs, DAEs. You can look at energy preservation. So these things also in the package. These are not, but could be. So BVPs are also a topic of interest, and PDEs with a method of lines. And you can use these methods for parameter inference. I have some plots in the end. Yeah, maybe one other place to point you to is there's a book written by my professor Philip Hennig and co-authors, which is a book about probabilistic numerics. So it covers probabilistic numerics for ODEs, but also for other numerical problems. So Bayesian quadrature, if you ever heard of it, or Bayesian optimization, also fall in this category of topics. So that's a good starting point also. Okay, so now about the actual Julia package. I'm more than halfway done, but now it only starts here. But the thing is that it's actually not very hard to use. So how do you use ProbNumDiffEq.jl? Basically, this is how you use ordinary diffeq.jl. You define your vector fields, initial value, time span, some parameters, the OD problem, then you just solve it with some solver. And to use ProbNumDiffEq.jl, you use a different solver. And then that is it. So the solution object is now not an ODE solution, but a probabilistic ODE solution. And it contains a bit more things. But in principle, this is what's happening. So that also means, so I really piggyback completely on ordinary diffeq.jl. That means that many things that work for ordinary diffeq.jl just work for ProbNumDiffEq.jl out of the box. Which also means that I don't have to write too much documentation because they already write a lot of documentation. So the getting started place here is probably the thing that I would point people to how to use my package sometimes. And the whole description of all of these keyword arguments that I have and so on, many of them just work. But of course, I also have docs that explain, well, mostly the differences of what's in this probabilistic OD solution. Maybe one fun fact also is in the SciML docs, you also find ProbNumDiffEq.jl. It's listed under third-party uncertainty quantification. I would argue it's actually a solver, but then Taylor integration is also there, which are also doing solvers. So maybe that's the place. Also, if you Google for ProbNumDiffEq.jl, you get to this homepage because SciML is better in search engine things. So what does the package contain? It contains, well, explicit and implicit solvers. EK0 is the explicit one. EK1, if you want to play around, is probably what you should use because it gives you nice uncertainties. You have different orders, as you would expect. You can use them by just putting the order in the brackets. You can make it quite large and it still works. So if you're interested in very high order ODE solvers, maybe that's something for you. You have, well, step size adaptation. We have dense output, so in between the points we get an interpolant, so not just a linear interpolation, because it is it is basically doing Gaussian process regression in some sense. So the object that we describe is a function, so we can evaluate it in between. This is also the output of a plot recipe, so that's nice. And you can solve well, Hamiltonian problems and add some callbacks for energy conservation. So most of the callbacks should just work from differential equations.jl. But of course, it's your discretion that the callback does something useful. And if you do the standard manifold projection thing, that's a very non-probabilistic way of projecting to manifolds. So there's also a probabilistic version of it. And then, yeah, you can see numerical error. So here I made the tolerance levels high enough that we can see something. And so how to interpret this is the 95% credible interval, and we believe the true function is somewhere in here. We can also sample from this object. So these are all samples that could be the true ODE solution that we computed. We have different priors. We have likelihoods to do parameter inference. And yeah, and there are some things that are missing. So on the engineering side, something like we cannot support DAE problems right now because in ordinary diffeq, either you're an OD solver or a DAE solver. We are both, but that doesn't work right now. And then maybe one bigger topic is adjoint sensitivities. That's just an open research problem. So how do you compute these things from a probabilistic numerics perspective? So yes, someone should write a paper about this. And then, yeah, I said we can use other filtering algorithms. They're not implemented. Would be cool. And yeah, a few more interface things. So just maybe 2 more things. When we talk about probabilistic, well, in ODEs, well, in the semi-L thing especially, there's always this question about methods needing to be super, super fast. And then on the other hand, when you look at probabilistic inference, then often maybe the doubt is that isn't it slow to be probabilistic about something? And I already talked about complexities earlier, so on paper, not. In practice, it depends. So here I just solve a Lotka-Volterra ODE, so it's low-dimensional, non-stiff. And if I compare myself to these super optimized ordinary diffeq solvers, then there's a factor of 100. On stiff ODEs, it's more like a factor of 10 for this specific one. Again, it's benchmarks, so it might depend on the problem. But then again, a factor of 10 is not too bad, I think, because we also, so in these methods, we compute strictly more, right? So instead of computing a vector for each location, we compute a vector and a covariance matrix. And this numerical uncertainty. And so if you wanted to get the numerical uncertainty in some other way, probably you would need to do more work. So I'm not surprised that the line's above, just a matter of how far above. And then there are also some examples where they're pretty similar. So for a second order ODE that is like 40 or 30 dimensional roughly, it's pretty close together. So I would say that there's the potential to be quite comparable and very useful for these problems. Maybe one last pointer. I only motivated the whole thing with numerical uncertainty. There's a bit more than numerical uncertainty that you can do with this. And so we had 2 papers on ODE, well, probabilistic numerics for ODE parameter inference that I would love to point you to. So in parameter inference, we want to find the parameters of an ODE such that it explains data. And maybe the one thing, like the one very clear example is if you have an oscillator and you start out of phase, then typically your standard least squares approach converges to a local optimum that looks like this, which is why people do multiple shooting and like many, many different things. And one of the things in this list of things that you could do is probabilistic numerics, maybe, because if you get if you see that it's a bad explanation, you can get uncertain about the ODE solution. And when you're uncertain about the ODE solution, what you end up doing is interpolating the data, because we solved the whole thing as a filtering problem. And if you just let the optimizer run, eventually you get to this output. So that was pretty motivating. We did that, well, this is presented in 2 weeks at ICML by a colleague, where we did that for a more interesting problem than an oscillator, so these Hodgkin-Huxley ODEs. And here's the explanation why. It's in the docs. Yeah. So yeah, the summary is ODE solving a state estimation, and you can actually solve it as a state estimation problem. Try it out. And yeah, please try it out. I would love to hear from you how it goes. Send me a message on Slack, open issues. Yeah, I also need a logo if you've seen it. So if you're excited about this, I'm very, very much looking forward to talking to you. Thanks.
Thanks. That was awesome presentation. Yeah, thanks a lot. I guess there will be quite some questions in the audience. Anyone? Okay. So I'll start from there.
Thanks for the great talk. You mentioned the in the last part the inverse problems, and I'm working on inverse problems. What I do if I want to tackle the inverse problem probabilistically, I would use a probabilistic inversion, like Monte Carlo or Hamiltonian Monte Carlo. What is the advantage of tackling the forward problem probabilistically to do the inversion from the get-go instead of just using a deterministic approach for the forward and then do the inversion probabilistically?
Could you expand a little bit on what you mean with doing the inversion probabilistically? So do you care probabilistic in the sense of you care about posteriors over the parameters, or in which sense probabilistic?
I solving the ODE or the PDE with the solver, so with a deterministic solver, and then combining your data to get the model parameters, but probabilistically. So that's what I mean.
Okay, yeah, that's a good question. I think that's one of these details that are often tough to communicate in probabilistic numerics. So there are many different things that you can be probabilistic about. Here we compute maximum likelihood estimates for the parameters, so a point estimate of the parameter. But that's basically because in this paper, so to get this, we need to define a likelihood of the data. I think for anything that you want to do, is it the maximum likelihood estimate, a map, or sampling from the posterior, you need a likelihood term to evaluate. And so the likelihood term can either be based on doing least squares with Runge-Kutta, or well, using Runge-Kutta and then just computing the mean square error for each individual location, or it can be a likelihood term that is aware of the numerical error, or that is a probabilistic model. So it's orthogonal. You can use this also for MCMC.
Okay. Thank you. Next question.
Thank you for your talk. I assume you have some form of like large deviation estimates. I'm curious how these compare to the sort of deterministic sort of worst case error bounds and error orders that one gets.
I'm not sure what you mean with large deviation estimates.
So like probabilities that it is such and such far away from the true ODE solution.
Mm-hmm. What we get out is basically a Gaussian process posterior. So that describes our belief over where we think the true solution is. And then the difference of that to worst case error bounds, I think, is that, well, the worst case error bounds assumes that, or from my understanding, typically that's a very theoretical mathematical object that people look at to prove that solvers converge. But normally when you have an ODE, it goes like this. So very quickly the error could be anywhere, but then you hope that if you make step sizes small, it still goes small. But this is probably a very bad estimate of something that is here. So in probabilistic numerics, we try to quantify the actual numerical error. So it's more of a, in this specific case error. Does that answer the question?
Yep, we have just 1 minute for another question, and then
I would love to
you can reconvene
after,
after the talk. Yeah.
Okay, so my question is just quickly considering slide 15. There was a plot where I didn't understand why. Exactly here. So we have these data points, and this is where we evaluate the ODE. Oh no, okay, it makes sense. Yes, sorry.
Yeah. So the dots here are to show the step sizes that the solver took, and in between it's interpolation.
Thanks a lot, Nathanael. I think it was. Let's give a big round of applause for this stellar work. Awesome. Yeah, I guess. There will be a bunch of people asking you questions right after. So don't hesitate to just catch him in the aisles. So